Alright, so in this particular video, we have a block that has a weight of 49 newtons that is resting on a frictionless surface here, and it has two forces acting on it. Here's F1, which is 10 newtons, that is directed 37 degrees above the horizontal here. And then here's F2, which is 14 newtons directed to the right. Alright, part A, B, and C, D, E. Let's knock it out all on the same slide here. Part A asks to find the mass of the block. So it's important here to notice the unit inside the block here. This is 49 newtons, and newtons is a measurement of force. In this case, 49 newtons represents the weight of the block, which is the same as F of G. F of G is also known as the weight of a block. Alright, so in order to do part A, we will simply set up F of G, which is the weight of the block, equals to mass times gravity. Therefore, to solve for M, we divide both sides by G algebraically. So we have F of G over G is equal to mass. But here, we have the weight, which is given, and that is going to be negative 49 newtons. It's the weight of an object or a block here is going to be pushing down on the surface. So that's going to be negative 49, and then the acceleration due to gravity at the surface, the Earth, is negative 9.8 meters per second square. So the negative signs will cancel out, and then 49 divided by 9.8 is simply 5 kilograms. So the unit for mass here is 5 kilograms. So it's important as you practice to pay attention to the number and the unit that's given inside each of these diagrams. So in this case, 49 newtons is the weight of the block, not mass, because mass has units in kilograms. So pay attention to the units as you practice, okay? All right. Part B asks you to find the net force acting on the block in the x direction. Well, we know that this particular problem, the block will accelerate to the right because both these vectors are pointing to the right. So we know that the acceleration in the y direction has to be 0. So the only possible direction that the block can accelerate is in the horizontal direction along the surface of the floor. Okay. So to do so, it's important to go ahead and draw your component to find the net force along the x direction. You should definitely identify the component for f of 1. F of 1 is a diagonal, so which implies that it has a fx component and an fy component. For now, I'll focus on the fx component because part B asks us to find the net force along the x direction, okay? So to do that, I will go ahead and label this dash component f1x. Whatever the hypotenuse is, just add a subscript that's in that direction. So if this particular force is F1, the horizontal component for that particular force would just be F1x. Well, if you look at this diagram carefully, you have two arrows that's pointing in the eastward direction or to the right. It is F1x and F2, okay? So it's important for you to find this component F1x. This is pointing right, F2 is pointing right. So therefore, the net force in the x direction would simply be F1x plus F2 because both of those vectors are pointing straight horizontal in the rightward direction. However, I know what f of 2 is. F2 is 14, but what I don't know is F1x, so we just have to do a little geometry. So by definition, f of 1x is the adjacent leg to this angle of 37 degrees. So because it is adjacent, we use cosine. So cosine is adjacent over hypotenuse, and therefore my adjacent in this case is f1x. Once again, hopefully your geometry is solid here. This is your adjacent leg to this particular 37-degree angle. And then the hypotenuse in this particular diagram would just be the diagonal, which is called f1. So to solve for f1, we would simply multiply both sides by to solve for f1x, we would simply multiply both sides by f1, so that will look like this. So f1x is simply f1, which is the hypotenuse times the cosine of theta. Well, f1 is given to us. We know that's 10, and then cosine of theta is also given to us, okay? So by now, hopefully you recognize that we just derived an expression for f1x, so we can substitute in for this particular statement. So again, the net force horizontal direction is f1x plus f2. We just calculate that, so I'm just going to substitute in the function here. So instead of f1x, I know that f1x can be substituted out for f1 cosine theta. And then I'm just going to plug in values. f1, which is 10, cosine is carried down. The angle is 37 degrees. And f2 in the diagram is a positive 14, which is pointing to the right. And if you simplify on the calculator, you should get a value of about 22 newtons, okay? So here in this case, it asks for the net force acting on the block. So the proper way to express this would be positive 22 newtons or 22 newtons, rightward or eastward, because I didn't see the word magnitude gets used. Okay, so if you really want to get technical, you should say positive 22 newtons or 22 newtons to the east according to this diagram. All right, let's go and crack out part C. Part C asks us to find the acceleration in the x direction. To find the acceleration in x direction, we need to use the net force in the x direction, which is equal to mass times acceleration in the horizontal direction. So algebraically, to find ax, we divide both sides by m to get ax by itself. Well, net force in the x direction, we just calculate in part B, which is 22 newtons here. That's pointing in the rightward direction. Mass, we found in part A, which is 5 kilograms. So all we have to do is plug and chug. Net force in the horizontal direction is 22 newtons. The mass is 5 kilograms. And then if you plug in 22 divided by 5, you just get a value of 4.4 meters per second square. Here I included the positive direction. Again, if you want to get all technical with what's the scalar, what's the vector. It says find the acceleration, and I didn't see that the fact that the word magnitude was used, so it's implying that it wants the actual vector itself. So in this case, the block will accelerate to the right, so it would be plus 4.4 meters per second square, and that would be my answer for part C. Part D asks us to calculate the distance required for it to reach a speed of 8 meters per second. Well, the quickest way I think to do part D here is to use this kinematics equation as time independent. Here I know VI is 0, so I'm going to cross that out. Therefore, to solve for delta x, which in this case is displacement, but the block is going one direction, so the magnitude of delta x is really the distance. And once again, the difference between displacement and distance is one's a vector, one's a scalar. And this problem only moves one direction, so really the magnitude in each of those values will be the same. Okay, so to get delta x by itself, I would simply divide both sides by 2a, so the 2a goes in the denominator. Well, Vf is given as 8 meters per second. That's the speed that we wanted. And then A we already calculated, which is 4.4. So we do 8 square, which is 64. And then 64 divided by 8.8, because 2 times 4.4 is 8.8. And then if you do that on your calculator, 64 divided by 8.8, you simply get about 7.3 meters. Here, I've chosen to use the absolute value of my displacement because the problem asks to find distance, and distance is a scalar, so there is no need to include direction here. So the distance traveled is 7.3 meters in order to get up to a speed of 8 meters per second. All right. Part E asks us to find the magnitude of the contact force exerted by the floor onto the block. Well, in order to do so, we just focus our attention in the vertical direction, or in the y direction for this one. So let's go ahead and draw all our forces in the y direction. So here I have net force in the y direction is equal to MAY, but this is pretty easy. The weight of the block, which is pointing down the page, okay, that's given to us. So f of g here is negative 49. I include the negative sign because the vector is pointing down, but it's up to you. You can put 49, and then just as long as you know how to interpret the 49. And then fy though, right, is a diagonal that's pointing down and right, so therefore the f1y needs to be pointing down. So it's important that you draw these components with the right arrow, aka directions. So f1y is pointing down. Now that I got these two vectors, I need to draw f of n. F of n in this case is the force exerted by the surface onto the block, which is in the y direction, or perpendicular to the surface. Here, I've chosen to draw Fn a little longer because I know that F1y is pushing down. Fg is also pushing down, so therefore the floor has to push back with the same magnitude, which suggests that Fn would be the bigger vector in this case. All right, so here's Fn, and then to really solve for Fn, we just have to focus and count all of our vectors or vector components in the vertical direction. Here I have Fn pointing up in the y direction, I have f of g pointing down in the y direction, and then I have also f1y pointing down. So really there are three vectors that you need to be accounting for. All right. But to find f1y, similar to what we did with f1x, we can just apply sine. The reason we apply sine for this one is because based on this angle of reference point, 37 degrees, f1y is the opposite leg. So f1y, because it is the opposite leg, we would use sine, because by definition, sine is opposite over hypotenuse in geometry. Opposite in this case would be f1y. The hypotenuse is your vector itself as f1. And if we isolate for f1y, we get that f1y is f1 times sine of theta by simply multiplying both sides by f1 to get rid of the denominator. All right, so if you do that, you should get a 10 times sine of 37, and then the magnitude, or excuse me, F1y is equal to negative 6 Newton. The magnitude is 6, but because it's pointing down, there is a negative sign there in front of it. Well, but that's not it though, right? The question asks us to find f of n, but, well, we know what f1y is, we know what f of g is, so f1y is pointing down, fg is also pointing down, and there's only one vector pointing up, so I like to say up equals the sum of down. But I'll do proper here. Here I've chosen to write the positive vector first, which is f of n. I want to minus it from f1y because f1y is pointing downward, which is opposite of f of n. I'm also going to subtract that from f of g because f of g, once again, is opposite of f of n. And notice here I already took care of the negative signs here in f1y and f of g. Ay is equal to 0 because the block is not allowed to leave the surface, so the acceleration occurs in the horizontal direction, not in the vertical direction. So do not plug in 9.8, okay? Do not plug in 9.8. A common error that kids will do is that you plug in Ay is equal to 9.8 because you're thinking of free fall, but these systems are not falling. They're just moving across a horizontal surface. So therefore, the acceleration in the vertical direction has to be 0. All right. So algebraically speaking, if we solve for fn, we need to move this negative f1y to the right side, which makes it positive. Same things with f of g. Here's negative f of g. Move to the right side equal sign, which makes it positive. And then I would plug in f1y as 6. Do not plug in f1y as negative 6 here because the negative sign has been accounted for already. So by the time you get to this point, you would only plug in the magnitude of these vector or vector components. So f1y, while it is negative 6, the negative sign has already been taken care of in the second statement. So therefore, I just plug in 6. And again, we know f of g is negative 49, but the negative sign is already stated, so we don't need to undo it or be redundant and state it twice. So f of g here would just be the magnitude of 49 newtons. So therefore, the f of n is 55 newtons, which makes sense. I mean, there's 6 pushing down, there's 49 pushing down, so therefore there must be 55 pushing up in order for the object not to accelerate in the vertical direction. Okay, so that is our answer for part E. All right, I hope that helps. Stay nerdy, don't be whack.